Hello everyone and welcome to our Capstone presentation. We are Team GAPS-COMM and our sponsoring company is iXblue Defense Systems. For this project we were assisted by our technical directors, Patrick Morin, Daniel Nugent, and Jeremy Peacock. Our team is made up of 2 computer engineers, Cruz Marcil and myself, John Hunter. Our team also has 2 electrical engineers, Kyle Keefe and Ariana Angeloni. Before we get started with our project, I will provide some background on our sponsoring company. iXblue Defense Systems is headquartered in France and specializes in design and manufacturing for the naval and land defense markets. One of their products is the GAPS device. GAPS stands for Global Acoustics Positioning System. The GAPS device is used to track the position of an underwater acoustic beacon. iXblue is looking for a system to manage multiple of these GAPS devices at the same time. This would allow for tracking an underwater unit over large areas. This is the motivation behind our project. Our project is a software and hardware prototype system that will allow the cooperative operation of multiple GAPS units. The system will track a beacon as it travels between the ranges of each GAPS device. Our best anticipated outcome for this project is to have a functioning software prototype as well as documentation for the software and hardware of the system. We intend to test our system with live data in the field, if possible, in the future. This is a list of the technical accomplishments that our team has completed this semester. We have completed a software requirement specification document outlining how the system is structured. We've also developed multiple flowcharts for the system and each individual software module that we will be developing. We have all familiarized ourselves with the Python programming language and the current working GAPS software system. Using the sample code provided by our technical directors, we have begun prototyping software components for the GAPS-COMM system. Our Capstone project will reduce the time spent during beacon configuration and management. Our project will also allow large-scale beacon monitoring, expanding the product use cases. This marketable feature will have a positive economic impact for iXblue Defense Systems. Our next speaker is electrical engineer Kyle Keefe.
Hi. Though my main priority from an electrical standpoint is to manage hardware requirements for this project, the abundance of code-centric work has seen to it that my responsibilities extend into the domain of software as well. I've managed connection to the GAPS device through both wired and wireless mediums, as well as created the spatial track modules, flowchart, and code. Firstly, the anticipated best outcome involves wireless communication between a CPU housing our software and at least 2 GAPS. To this end, I had to search for a pair of wireless routers with which I could set up a local wireless network. The selection of these was not a very difficult process, as they were needed mostly for testing purposes, and considering that there's only 1 GAPS connected to each router at any given time, requirements in terms of bandwidth and speed were fairly low. However, the onboard programming of the routers required connection to a modem for setup, and this lack of necessary hardware provided a temporary obstacle to establishing the network. It turned out later that a wired connection to an Ethernet port on my dorm room wall was sufficient to bypass this software block, and all that was left to do was set up a local network on one router and designate the other as an extension. So far, both wired and wireless devices are discoverable to each other on this network while being connected to separate routers, so that all that is left to do is test TCP connection as well as the sending of commands to the GAPS itself. Next, I created the initial flowchart for the spatial track module. As one of the more complex modules in our software, spatial track required several redesigns after discussions with our technical director, and its chart saw multiple iterations. Its goal is to accept positional data passed to it by the data buffer, then both filter out erroneous data and calculate beacon speed and direction. It would originally use those calculations to determine whether or not a beacon was exiting one GAPS' range and entering another's. But it was decided that this would be better left off to the beacon handoff module, and this functionality was removed. After Travis and I settled on the final flowchart configuration, I began to work on the code itself. The process involves a simple calculation of speed between the two most recent data points, and it compares this speed to a range of user-entered ones. If the velocity or speed is outside this range of expected values, then the point is marked as invalid and will not be used in the final velocity calculation. To do this, absolute positioning data in the form of latitude and longitude is acquired and put through the Great Circle calculation, which determines the distance between 2 points on the Earth's surface. Then, data points from a designated time window, for example, all points from the last 7 seconds that have been marked as valid, are taken. The Great Circle calculation is performed again, and both speed and direction are calculated and averaged among them. This software module also saw a significant redesign in collaboration with Cruise to ensure compatibility with the Pandas data frame that was used in the data buffer. This redesign made it so that valid and invalid marks, as well as speed and direction, could be appended to each individual point in the data frame, instead of simply dealt with internally in the module. Before May, we'll have to test the local network using the actual GAPS, as I mentioned. Additionally, we need to code a beacon handoff module, as well as improve the plotting of our data to reflect valid and invalid designations. There's much documentation left to be done, as a set of deliverables for iXblue, and this includes a thorough software design specification document. A main controls file and GUI must be developed to tie all of these software modules together, and testing of both individual modules and the software as a whole must be continued. At-sea testing of the product as a working prototype is a reach goal should the ABO be accomplished with time to spare. With that, I'd like to hand the presentation off to our next speaker, Cruz Marcel.
Hello, my name is Cameron Cruz Marcel, and this semester I was able to communicate with the GAPS device using TCP communication, and I also created several software modules and flowcharts to go with them. To get data from the device, we decided to use a TCP connection. Python Sockets has an easy-to-use library that we decided to use. This connection is perfect for this application because it is reliable and no packets will be corrupted or lost during transit. In order to configure the GAPS device, URLs need to be filled with the correct values that are given by user input. This was achieved by using Python's URL lib. Known URLs are taken and parsed, then rewritten with the correct values. Once the correct URL has been created, it is then opened, and through Python, a confirmation message will be read. Overall, this task wasn't too hard to achieve, but it did take some time. For the data parser/data buffer, Python's pandas library was used. This library allows the creation of a data frame that makes storing and using the GAPS data easier. The difficulty in this task came from learning how to use a data frame. Patrick Moran gave our group a sample of code that had already created and parsed GAPS data into a data frame, and the sample code needed to be modified to work on continuous reads of data and include a spot to store calculations. The full modification of the previous data parser was a success, and the data parser starts by reading in data from an input buffer, where it is then split into separate lines of data and stored into the data frame based on the time index that is given from the GAPS device. To configure beacons, the previously explained URLs are used to write new configurations to the GAPS. To correctly configure a beacon, there are 3 steps that need to be followed. First, you write the configuration to the GAPS device, then wait for a confirmation that the update has occurred, and lastly, the configuration should be read to ensure that correct values were written to the GAPS. The configurations can deal with things such as interrogation modes, frequencies, and reply codes, and in total there are over 20 different variables that can be configured. This task was slightly difficult due to the number of configurations, and also because the old configuration must be stored and then changed depending on the user input. There are several key accomplishments that I plan to make before April 16, 2021 to achieve the anticipated best outcome. Our team has split up the software modules to allow for separate groups to work on these modules at different times, and as a result, some of these modules may not be completely compatible with one another and may need to be modified to function as a whole. The most important software module, the beacon handoff, has yet to be created, and this will require a lot of very specific scenarios to be tested to ensure that beacons will be tracked and passed to other GAPS devices correctly. Also, the main file that will use the software modules will need to be created. This will be a graphical user interface that is based on the iXblue web-based interface, and our graphical user interface will consist of several user inputs, commands, and a simple graph. A test graph has been created but will need to be modified to better illustrate the locations and ranges of the GAPS devices and beacons, and software documentation will continuously need to be updated, and this will allow for other people to take over the project once we have finished with Capstone, and also give them a clear reason as to why we made certain decisions in our software. And I would like to introduce our next speaker, Ariana Angeloni. Thank you.
Just as a refresher, this is the general diagram for the system we'll be creating, where we're taking multiple gaps and implementing them into a network. And the control software is just the multiple modules we'll be using and coding so that the network works. And the control and data interface shown is just the user inputs, things like that. So as I was just introduced, my name's Angie, and I'm the second electrical engineer on the team. Most of my technical contributions center around documentation. So the listed SRS and SDS are both documents where we go into very fine detail about how the modules we'll be creating work, as well as flowcharts that we've been making along the way and working on. That details exactly what data goes in, what data comes out, and the whole process of what goes on in between. Trello is the task and schedule management system that we've been using. So how I can explain, I will be going into a little bit in depth on that a little bit later. And just a general overview, the tasks that I'm going to be doing to reach the anticipated best outcome will be finishing the SRS. That's been a living document. So as we continue and test our code and learn more about how the system needs to work, and fine-tune things, we need to incorporate that into the documentation so that if someone needs to go back into our work and see how or why something works the way it does, it'll all be laid out perfectly there. Another important thing is to make sure that all of our documents have uniformity, so things that are named the same way in every document so that it's not very confusing for anyone trying to read. And that includes the final hardware and software documents we'll be creating, the final reports, including all the test data, if time allows, and any instructional manuals that we can create for the modules. I'll also be helping with the 2D plotter software. I'll get into that a little bit later, as well as the GUI that I mentioned on the last slide. And if we get to a final system, I'll be also helping with the testing. So this is kind of just an example of what the SDS and the SRS look like. This is an excerpt from the SDS. So I just took a table of contents so that you can see what types of information we're putting in these documents. So as always, just the introduction, and then we kind of go into detail about the data buffer and the data parser. The data buffer and the data parser written here are two of the modules we'll be creating, and underneath each of those topics, we'll be explaining the inputs, their outputs, what type of operations they'll be doing, and also the formats for the data that each one takes in, which will be important later on if someone wants to understand how that specific module works. Here I have an example of one of the flowcharts that we've been coming up with as the project goes along. This one specifically is about the general hardware. So again, you can see the two gaps. We've been basing everything off of two gaps because once we can get two gaps to work together in a network, it should be pretty easy to expand to more. So here you can see two gaps that are connected directly using wires to the gaps box, which is kind of a box that tells the gaps how to work, what to do. and each of those are connected to a GPS, which is very important in an acoustic tracking system. And then each GAPS box is wired to a Wi-Fi router, which is then using a Wi-Fi connection connected to another main Wi-Fi router, which is wired to the GUI, which is kind of how all of the controls and commands go out. And the beacon is just shown here because the beacon is communicating with each GAPS, whichever GAPS is closest to it, using an acoustic connection, so that we can track the beacon. And here's an example of the Trello system we've been working. How we've been organizing these tasks are future objectives, so things that we need to get done but don't really have a due date, current tasks, which as you can see may or may not have a due date, and completed tasks, things that we've already done, so that we can keep track of how we are, where we are in the project, how we're progressing. And as you can see, each task is assigned, quote unquote, to one or more team members so that we can keep track of who's doing what. It's easier to see whose tasks are listed under their individual contributions. So as for tasks that need to get done for the anticipated best outcome, the SRS definitely needs to get finalized. Here you can see an excerpt of the SRS. So it's very long, very detailed. We go into the purpose and the document conventions of the overall project, as well as some other things, some references. We link there's actually a GAPS user manual that iXblue provided that's linked in this document, just so that it's kind of a complete package, so that it's not a ton of different documents that are very confusing. And then we also go into the overall description of the project, what's going on, what the GAP network is, and then some other fine-tuning details as in software or system requirements and things like that. So one of the other things that I mentioned I would be having to ensure for the anticipated best outcome is that all of our reports are uniform, so that it's easy to go from one to the other. Everything is named the same, it's not confusing, so that whoever needs to understand our system can do so easily. Another thing that I mentioned was the 2D plotter software. Here's just a general vague example of what a 2D plotter software does. Ours might not look exactly like this, but it's basically going to be an XY axis of latitude and longitude with dots showing where the beacon, whichever beacon we're tracking, is. And probably on here is going to be each GAPS, because we should also know where each GAPS is, because as we saw before, they're connected to a GPS. Another thing that we'll be developing is the GUI, the user interface. This is an example of a GUI that iXblue already has in place. So we will be aiming to get something that is similar to this, the same colors and just some explanations here, the logo button, the command button, things like that. It also has the status of each beacon or item that you're tracking, as well as menus and things like that, everything that a user interface would need. So a user could go into this menu and set their preferences and things like that. Then this would send all the information to the GAPS system. And as our next speaker, I'm going to be introducing Travis Hunter, and then he'll take it from here.
Hello, I'm John Travis Hunter, a computer engineer. I've been working on software documentation and flowcharts, as well as software development on the spatial track and the two-dimensional plotter modules. On the right is a two-dimensional plotter from the GAPS system. This tracks the longitude and latitude of a GAPS unit and two beacons. You can see that the GAPS unit is attached to the back of a boat that is moving in a spiral pattern. For my individual technical contributions, I've been prototyping a two-dimensional plotter that displays live locational data to the GAPS operator. I've also been helping my team members in the development of the Spatial Track software module. This module processes the position and speed data of the GAPS and the beacons. The Spatial Track processes each data point and calculates the speed, direction, and validity of the data point. The main tasks I individually have to finish in order to achieve the anticipated best outcome are listed here. I will finish the development of the Spatial Track, two-dimensional plotter, and the beacon handover modules. When we have an operational system, We will test our product with the live data, hopefully in the field. At the end of this next semester, we will provide documentation that will support the future of the project.
As far as the team accomplishments that we need to be getting done in the next couple months to be able to achieve the anticipated best outcome, something that we're aiming to do is be able to track beacons using the GUI that we develop, as well as keeping track of everything we're doing using a software and hardware document. So each document will be focusing on different things. The software document is mainly just to keep track of anything that a user would need to know about the modules we develop, maybe some preferences, things like that, anything that they would need to know before running the network. And a hardware document is just about the same things, preferences, the things that a user would need to know before being able to use the GAP network. We also hope to be able to test the final version of the software as long as all the modules are working, have been coded, just to see if they can work together. We have been able to test our software on an actual GAP network or GAP system that iXblue has provided, and then we will be providing a final report including any test data, everything that we've been doing, just so that it's a comprehensive document on how the project went, and our logic and our reasoning, things like that. Finally, we'd like to acknowledge some people who made the program function as well as it did, or as well as it is functioning. Two very important people are the technical directors, Patrick Moran and Daniel Nugent from iXblue. They've been graciously lending their time to helping us understand the current GAP system so that we can further develop the GAP network. They've been crucial in our understanding of the system so that we know what next steps we have to take. The Capstone Program Director, Dr. Sunak, has also been helpful in keeping us on track on documentation and things like that, and also helping us work with such a great company such as iXblue. And also, someone we need to acknowledge is the assisting technical director, Jeremy Peacock, who has been consistently lending his time on once a week so that he can answer any questions we have, has been very flexible with what we need, and who has been keeping track of our program since the beginning. So we just want to say thank you, and this is the end of our presentation. We hope you liked it, and that it was easy to understand.